Welcome to my Unit 6 Network Graphs presentation, titled Connected Intelligence, Mapping Fragile Hierarchy and Robust Connections. My name is Arawa Moron-Thodoon-Jalade, and this is Data 625, Section 9043 for Spring 2026, instructed by Dr. Alan Westcott. Our dashboard highlights a critical trade-off between two architectural philosophies. At the top, we see a robust mesh, a system engineered for redundancy and endurance. While redundancy is often viewed as an inefficiency, here it is the primary driver of resilience, providing multiple fail-safes that ensure the network survives localized disruptions. In contrast, the bottom visualization represents a fragile hierarchy. This system prioritizes efficient routing and clear centralization, but that efficiency comes at a cost. The high degree of centralization creates gatekeeper nodes that increases systemic risk. If a centralized hub fails, the entire structure becomes vulnerable, proving that in network design, maximum efficiency often leads to minimum robustness. Let's first examine the fragile hierarchy, a structure governed by critical gatekeeper hubs. In this network, Nebula and Starhawk command the highest betweenness centrality scores at 0.72 and 0.68 respectively. In cybersecurity terms, these scores serve as a direct metric for network fragility. The higher the score, the more catastrophic the impact if the node is compromised. Consider a business case where the Nebula node is hit by malware and forced offline. Because this is a hierarchical bottleneck, every node in that cluster becomes instantly isolated, completely severed from the Starhawk hub and the rest of the enterprise. The inverse is also true. Disabling Starhawk paralyzes half the network's communication capabilities. To mitigate this systemic risk, my recommendation is to transition from this fragile state toward a robust circular reinforcement framework. By engineering redundant connections between second-level tiers, Cybertron, Nova, Nebulon, Galactica, Astroblade, Quantum, Pulsar, Eclipse, Hyperion, then back to Cybertron, create a continuous fail-safe loop. This circular architecture ensures that if a primary gatekeeper fails, the network can reroute traffic through the backbone, maintaining operational continuity even under a targeted attack. Now let's contrast the fragile hierarchy with the robust mesh. In the previous model, we saw gatekeepers with dangerously high centrality scores, averaging 0.7. Here, we see the opposite. In a robust mesh, even the primary nodes maintain significantly lower betweenness scores with an average of 0.19. This is not a lack of influence, but rather a result of decentralized architecture. Because the system is built with redundant pathways, nodes can communicate across hub boundaries without relying on a single bottleneck. By distributing the flow of information across multiple connections, we effectively eliminate the gatekeeper risk. If any one node is compromised in this mesh, the impact is localized, not systemic, allowing the rest of the network to remain fully operational through its inherent structural resilience. In conclusion, to secure your network's future, we must transition from a fragile hierarchy dependent on high-risk gatekeepers to a robust mesh that prioritizes redundancy and decentralized workflow. By engineering structural resilience through circular reinforcement, we eliminate single points of failure and ensure operational continuity even under targeted disruption. Thank you for joining me in my Unit 6 Network Graphs presentation.